Okay, next section is 12.4, which is your applications of double integrals. So, any sort of application of calculus is usually physics. So we'll get a little bit of physics in here, and I'll do my best to explain some of these concepts here. But the first application that we're going to look at, oops, what just happened there? Okay, is talking about density and mass. Okay, so we are going to think about a two-dimensional shape. And this is called a lamina or a planar lamina. Okay, so this is going to be region D. D is a lamina, which means that it has negligible thickness and variable density. Okay, so you can think of that as maybe electric charge on a plate. You can think of that as like population in an area. Okay, where the thickness there would not matter. It's much more just that surface area there. Okay, and then remember, density is mass over area, which of course then makes mass equal to density times area. Okay, so back to our planar lamina here. There will be some point in there that will be, well, I don't need to make it at the center. I didn't really mean to. You can go back to your infinite little rectangles in this region that are delta x by delta y, and then we'll add to it the density function, which is rho. Okay, so every xy coordinate has a specific density that would go with it. Okay, so what we can do is, if we want the mass of a single rectangle, we'll have whatever the density is in that rectangle. Okay, and again, those asterisks just mean that we're somewhere in the rectangle. Okay, and our rectangles are going to get so small that it doesn't really matter where you are in the rectangle. Okay, times delta x times delta y. So they'll get your density times your area. Okay, if we want the mass of the entire thing, then we could sum all of the different rectangles together. Okay, and that might, again, if we go back to our examples, if we're talking about electric charge on a plate, that would give us the total charge. Okay, population in an area, if we're doing like population density times the area, that gives you the total population. Okay, so your mass, isn't always mass. It could be your population mass. It could be a total electric charge, something like that. Okay, and then as we know, oops, I'm sorry, I left out an important part there. It would be approximately equal. Okay, so it would equal the limit is delta x and delta y go to 0 of that whole summation. Okay, which again, we know we can represent that as an integral over d of our density function. Okay, so let's get some examples here. starting with number 6, we're supposed to find the mass. And then we'll get to center of mass. Yeah, okay. So first we're just going to find the mass of the lamina with density rho. And in this case, D is the triangular region. Enclosed by x equals 0, y equals x, 2x plus y equals 6. Okay, and rho xy is x squared. Okay, so the density is only dependent on x. Okay, so let's first draw our region. Okay, so we want the boundaries. X equals 0, y equals x, and 2x plus y equals 6. So when x is 0, y is 6. When y is 0, x is 3. Like that. Okay, so they would intersect at oh wait, hold on a second. I don't like how I drew that. Looks like, because I drew it wrong, that's why I don't like how I drew that. Okay, so it looks like this. Okay, and they would intersect at 2, 2. Okay, and then we get 0, 0, 0, 6. So this is our region. Okay. So all we need to do then is your integral. Let's see. We can, obviously we can do it a couple different ways here. We can do x goes from 0 to 2, and y goes from, we're bounded below by y equals x. Oops, I got to switch those, right? And above by y equals 6 minus 2x. Let's do it that way. Okay, I'm going to move this over here. Okay. Oh, that didn't go very well, did it? I tried to get fancy there. Let me just redo it. All right. 0 to 2 needs to be on the outside. X to 6 minus 2x needs to go on the inside. Rho is x squared, and then we'd have dy dx. Okay, so that would give us the mass. Okay, so then that would be our integral from 0 to 2 of x cubed, x squared y, where y goes from x to 6 minus 2x. Okay, so our integral from 0 to 2 of x squared times 6 minus 2x minus x squared times x. So that'd be our integral from 0 to 2, 6x squared minus 2x cubed minus another x cubed, so minus 3x cubed. Okay, so now we'll have 6x cubed over 3, so 2x cubed minus 3/4 x to the 4th from 0 to 2. So we would have 2 times 8, which is 16. 2 to the 4th is 16, times 3/4 would be 12. And then the zeros won't matter, so we get 4. Okay, so there's our mass. Okay, the next one we're going to talk about is moments. Okay. And you might have learned about moments in physics before. Moment is force times distance. Moment is the reason that when you are trying to use a wrench, you hold on to the very end of the wrench and turn rather than trying to turn closer to the bolt that you're trying to turn, because you get a bigger moment because you're increasing that distance there using the same force, and so you're able to move the bolt. Okay. It's also like levers, which is something similar. If you push on the end of the lever as far out as you get more of a moment to move something. Okay. For a lamina, since it's actually the moment is the mass times the distance. Okay. And it's the distance to a line, and most often that's an axis. Okay. Your moment is kind of the tendency for the region to rotate. Okay. If you just kind of thought about it here, if I scroll up here, if I think about this triangle just sitting on top of the x-axis, it has a tendency to rotate around the x-axis. If you kind of think about if it was just, if this was vertical in space, and this is the ground, and we just have this triangle kind of on the ground, and you're it's going to fall because of the moment. Whereas if you had something that was more centered around the x-axis, like a little circle here or something, and I release it, there's not really a tendency for that to rotate because it's kind of balanced. So we'll kind of talk about that a little bit. And then it makes sense then when you talk about the equation. The moment about the x-axis is your limit is delta x goes to 0 and delta y goes to 0 of the sum from I equals 1 to m, j equals 1 to n, y star ij, rho xij, yij times your area. Okay. In other words, the farther away it is from the x-axis, so the higher y is, and the more dense it is, the higher the moment's going to be. Okay. So really dense points that are far away from the x-axis increase our tendency to want to rotate around the x-axis. We want to get that spin going. Okay. And this is much easier to understand as just your double integral over d of y times rho xy. Okay, and then similarly, we can have our moment about the y-axis. And that's going to be your summation of your x star. Okay, so now points that are farther away from the y-axis are going to have more of an impact. Okay, and then also times your area. So our double integral over d of x times rho xy. Okay, and now we can find the center of mass then for our guy up here. Okay, I'm sorry, our moment. Sorry. And what we should see is that the moment around the x-axis is bigger than the moment around the y-axis. So if you think about the tendency for this triangle to rotate around the x-axis is much more than if the y-axis were the ground and I let go of the triangle, for it to rotate around the y-axis. Okay, it's kind of a little bit more settled in there, I guess. I don't know what the way to kind of think about it, but hopefully you can see that when we're looking at the x-axis, there are more points that are farther away than around the y-axis. okay? And what does kind of help your moment about the y-axis is that your density increases quadratically as x increases. So we've got the densest points are over here, okay? So that kind of helps with your moment about the y-axis, but it also kind of helps with your moment around the x-axis too, because they're not right on the x-axis either. So anyways, let's find these. So back to number 6. Number 6, we're going to find the moments. Okay, so basically all we're going to do is the same integrals that we did before, but in the for the moment around the x-axis, we're going to throw a y in there, and for the moment around the y-axis, we're going to throw another x in there. Okay, because this is the only thing that makes this different than your mass integrals is that distance from the axis. Okay, so our moment about the x-axis is going to be, again, the integral from 0 to 2, integral from x to 6 minus 2x of x squared times y dy dx. Okay, so integrate that with respect to y. And evaluate it from y equals x to y equals 6 minus 2x. And then we'll have let's see, let's do it x squared. I'm trying to think of how I want to simplify this. Let's do x squared over 2. We'll just go with it. That'll be x to the 4th over 2. Okay, so expanding out our 6 minus 2x, we'd have 36. So we'll have 18x squared. And then minus 2ab, so minus 24x times x squared over 2. So minus 12x cubed. Okay, and then here, 36 minus 24x plus 4x squared. So then we'll have plus 2x to the 4th. And then we're going to subtract from that an x to the 4th over 2. Okay, so then we've got our integral from 0 to 2, 18x squared minus 12x cubed plus 3 halves x to the 4th. Okay, so we've got 8x cubed over 6, so 6x cubed, minus 12x to the 4th over 4, so 3x to the 4th, 3x to the 5th over 10. And we're going to evaluate that from 0 to 2. So we'll have 48 minus 48, right? Plus 2 to the 5th is 32, so 96 over 10. So the 48s cancel out, and we have 48 over 5. That's our final answer. Okay, and then we'll do the same, something similar for a moment around the y. So it's going to look just like our area, or I'm sorry, our mass one. But we're going to put in that extra x. So it's x times rho, so x times x squared would be x cubed dy dx. Okay, so our integral from 0 to 2, we'll have x cubed y, where y goes from x to 6 minus 2x. Okay. So x cubed times 6 minus 2x minus x. So 6x cubed minus 3x times x cubed, 3x to the 4th. So we'll have 6x to the 4th over 4, so 3x to the 4th over 2, minus 3x to the 5th over 5, evaluated from 0 to 2. Okay, so we've got 24 minus, we've got 3296 over 5. Okay, so this would be 120 over 5 minus 96 over 5, so we get 24 over 5. And just like we expected, the moment about y is less than the moment about x. Okay? All right, moving on to our next application is center of mass. Okay, now this is a pretty important one. The center of mass is kind of like it's your average x and your average y, but also taking into account your densities. So basically, if you're to take this flat planar lamina and try to balance it, okay, so like balance it, that point, that balance point is x bar, y bar, okay? So it takes into account the area, but also the density. So like if this were something that were super dense to the right, then maybe the center of mass would be like way over here, okay? Because like it's super heavy here and really light over here. And so to balance it, we put it like here, okay? So wherever that balance point is. Your formula for center of mass is x bar is the moment about y over the mass, and y bar, as you could probably guess, is the moment about x over the mass. Okay, so if we go back to number 6 again, this is going to be super easy because we've done all the work that we need to do. For number 6, find the center of mass. Okay, so our x bar would be the moment about y over m, which was 24 over 5. And if you remember, mass was 4. Okay, so that's 6/5. And then y bar is the moment about x over m, which was 48 over 5 over 4. So it's going to be 12 over 5. Okay, so if I go back up there, this is at 2 and 1. So your x bar was 6/5, so x bar would be about right here. Trying to get about 6/5. Okay, and y bar is 12/5. So that would be a little bit over 2. Okay, so right around there, that point at 6/5, 12/5. That's your center of mass. Whereas I had to turn this over flat and try to balance it on the tip of my finger, that's where I need to put my finger. Okay. And then it wouldn't rotate. Okay. If you were to shift it, sorry, let me go back up there. If you were to shift it so the center of mass was at the origin, then it would have no moment. There's no tendency to rotate, right? If we go back to the formula, if x bar, y bar is the origin, then that would mean the mass about, or the moment about y and the moment about x are 0. Okay? So it would have no tendency to rotate. Nice and situated without any sort of external force. Okay? Then we're almost done. So the last one is your moment of inertia. It's sometimes called your second moment. Okay, and that's basically, okay, if it is rotating, how much will it take to resist the rotation? Okay, or how much will the rotation be resisted, I guess. This is one that I think it's a little bit hard to grasp. But anyways, it's going to look familiar. I'm going to skip the summation one. It's just the same thing, but around x, we do y squared, rho xy. And your moment of inertia about y would be x squared, rho xy dA. Okay. One example, and I found this on Wikipedia when I was looking for examples of applications of moment inertia, is if you think about a figure skater, how when they're doing a spin, they pull their arms in, and that is to reduce their moment of inertia. They want to spin. So they're going to pull their arms in so they have a smaller moment of inertia, because then that means that those y's and x's are smaller. They have a smaller moment of inertia, so they'll continue to spin. If they put their arms out, they increase their moment of inertia, and it decreases their resistance. I'm sorry, it increases their resistance to that spin. Okay, so they would spin slower. So I think about that. Yeah. Okay. We also have another one, the moment of inertia about the origin. Okay, so we can take the moment of inertia about a point too, and that would be x squared plus y squared rho xy dA. Okay, and one interesting characteristic is that the moment of inertia about the x-axis plus the moment of inertia about the y-axis equals the moment of inertia about the origin. Okay. All right, so we are going to do an example, our same one that we've been using in number 6. So our moment of inertia about the x will be our integral from 0 to 2, x to 6 minus 2x of y squared, x squared dy dx. So we'll get that one. And I'm also going to do over here the moment of inertia about the y, okay, which is the integral from 0 to 2, integral from x to 6 minus 2x, y squared, x to the 4th. Okay, and then we'll talk about the moment of inertia about the origin. Oops. Okay, and you can see how that would work then, right? Because we can split that integral. And that would be dy dx. Okay, so you can see exactly why that relationship exists. Okay, so we can do that either way. I'm not going to go through all the work for it. You could definitely do it on your own to prove that it's true, but you could go ahead and do this integral, or you can just add up the ones that we're going to get above. Okay, so anyways, our moment of inertia around the x-axis, we will have the integral from 0 to 2. We're integrating with respect to y, so y cubed over 3 times x squared from y equals x to y equals 6 minus 2x. So we would have our integral from 0 to 2 of, let's see, I'm going to just take that x squared over 3 out. And we'd have 6 minus 2x cubed, okay, minus x cubed. Okay. Oh, and I left that blank in my notes. I'm not sure why I did that. Probably didn't want to keep doing the work there. Let me think there's an easy way to do that. I think I'm just going to leave that for now. I think I picked one out of the book that the book didn't necessarily finish. So you could do that. I don't know that there's any obvious u sub here. We could expand this all out. It's kind of a mess. but that's probably what we'd have to do here. Yeah, I almost think that's what we would have to do. Okay, but let's go over to the moment of inertia about the y. So we would have the integral from 0 to 2 of x to the fourth y, evaluated from y equals x to y equals 6 minus 2x dx. So we'd have 6 minus 2x and then minus x. I'm just going to write 6 minus 3x. Okay. So then we would have 6x to the fifth over 5 minus 3x to the sixth over 6. Okay, evaluated from 0 to 2. Okay, so the zeros aren't going to give us anything there, but the 2's will. So we'll have 32 times 6, 192 over 5 minus, well, x to the fifth is 64, so it'd be 64. Okay, so we'd have 192 over 5 minus 320 over 5, which is negative 128 over 5. Okay, and like I said, over here with the x1, we would have to integrate it. So we could expand that out by doing 6 minus 2x cubed, then subtract the x cubed from it, distribute your x squared over 3. It's not impossible. It's just I'm not going to waste the time in the video to do it. You could use your calculator to do it too to see what you get. The setup's the more important concept here. So, okay, but there you go. There's section 6.4.